This is a revision video on quadratic formulas and completing the square. The goal is to remove a few common confusions and help you check whether there are any algebra gaps you may need to revise. We will look at two versions of the quadratic formula, the ABC formula and the PQ formula. Both formulas give the roots of a quadratic equation. The PQ formula is commonly used in German-speaking education systems. The ABC formula is used when the equation is written as ax squared plus bx plus c equals 0. The PQ formula is used when the coefficient of x squared is 1. So the equation is written as x squared plus px plus q equals 0. To get from the ABC form to the PQ form, we divide the whole equation by a. This gives p equals b on a and q equals c on a. In other words, the PQ form is the normalized version of the quadratic equation. The PQ form is especially useful here because it makes completing the square cleaner. We will derive the PQ formula, and that derivation will show us how completing the square works. On the previous slide, we saw that the PQ formula applies to the equations in the form x squared plus px plus q equals 0. Now let's derive that formula. The idea is to turn the two x terms, x squared and px, into one bracket squared. This is useful because once x appears inside one squared bracket, we can solve by taking a square root. This process is called completing the square. Start with the general bracket squared, the quantity x plus m squared. Expanding it gives x squared plus 2mx plus m squared. To match x squared plus px, the middle term, 2mx, has to match px. So 2m equals p, which means m equals p on 2. This is why the bracket becomes the quantity x plus p on 2 squared. But this bracket squared is not just x squared plus px. It also contains the extra term p on 2 squared. So to get back to x squared plus px, we subtract that extra term again. This gives us the quantity x plus p on 2 squared minus the quantity p on 2 squared equals x squared plus px. On the previous slide, we found a way to rewrite x squared plus px as one bracket squared. Now, we substitute that rewritten form into the PQ form equation x squared plus px plus q equals 0. After substitution, x appears only once, inside the bracket. We then move the remaining terms to the other side, take the square root and subtract p on 2. The result is the PQ formula. The ABC formula can be derived in the same way. This means that both quadratic formulas can be understood as coming from completing the square. On the previous slide, we derived the PQ formula, which gives us the roots of the quadratic equation. But the important skill from the derivation is completing the square. Completing the square does more than lead to a formula for the roots. It rewrites a quadratic expression as a bracket squared plus whatever is left over. For x squared plus px plus q, the completed square form is the quantity x plus p on 2 squared plus q minus the quantity p on 2 squared. This is useful because it can make the structure of a quadratic easier to see. For example, if the completed square form is the quantity lambda minus sigma squared plus omega squared equals 0, then the roots are lambda equals sigma plus minus I omega. This is the complex root case. But completing the square does not always give complex roots. If the completed square form is the quantity lambda minus sigma squared minus alpha squared equals 0, then the roots are lambda equals sigma plus minus alpha. This is the real root case. Overall, completing the square helps us see the structure of the roots more clearly. In practice, this form can make the roots much quicker to recognize.